Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 938, range sum of BST. After that, we'll cover two actual variants of the original question that Meta asks, and I will say that one is much, much harder than the other. But without further ado, let's get into it. Okay, so we're given the pointer to the root node of the BST. Here, that's node 10. We're also given a lower and upper boundary. Looking at our example on the right-hand side, we have a lower boundary of 6 and an upper bound of 10. And we want to add up all the nodes whose values are between this range. Going back to our example, node 7 is obviously within the two boundaries. It's in between these two numbers. So is node 6 and also node 10. An important thing to note here is that the range is inclusive. So that's why 6 is included and 10 is included. The sum of all those three numbers is 10 plus 7 plus 6, and that gives us 23. This number is our answer, and we simply return that. Okay, so as it turns out, there are three ways of solving this problem, and they all differ in the way that we traverse this tree. The first one is using in-order traversal, in which we traverse the left subtree recursively, and then on the backtrack, process the current node, and then after that, process the right subtree. Okay, let's go over it very quickly. So we start at the root, right? We want to recurse to the left subtree first, which brings us to 5. We want to do the same thing, which brings us to 3, to 1. And from here, we go to the left of 1. There's nothing there. So that's one of the base cases. We'll just backtrack up to 1. And here, we will next process the current node. We ask ourselves, is 1 in between 6 and 10 inclusive? It's obviously not. Thus, we'll explore the right subtree, in which case there's also nothing there. Let's backtrack all the way up to node 3. Up here, we do the same thing. We process the current node. Is it between the range? No, it's not. There's nothing to its right subtree either. We backtrack to node 5. Here, same deal. You'll eventually go into the right subtree. On node 7, remember, you want to explore the left subtree first before anything else. That brings us to 6. There's no left child of node 6, so we process the current node. Finally, we answer our question of, yes, 6 is indeed between the range of our lower and upper bound. Fantastic. We can add that to a variable called sum, and we'll have 6. There's nothing to its right. We backtrack up to 7. We process the current node to say, hey, 7 is also in between our two ranges. Let's add that to our sum to get 13. And you'll note that an in-order traversal of specifically a binary search tree explores the nodes in ascending order. First, we looked at 1, and then 3, 5, 6, 7. After that, we will go to 10, 13, 15, 18. Ultimately, we'll just add the 10, because it's within the range inclusively, and we'll get 23. We will explore 13, 15, 18, and those are obviously greater than our upper bound. We're left with the answer. This solution works, but it will always result in a big O(n) time complexity. That's fine, but we can do slightly better by taking advantage of a BST, in which a BST is a tree in which a node's left subtree's values are strictly lower than it, as you can see. Take this 10, the 5 is lower than it, so is the 7, 6, 3, 1, etc. And conversely, the node's right subtree's values are strictly greater than it, namely 15, 13, 18. So let's move on to our second solution. So what if we still used recursion, but instead with pre-order traversal, in which we explore the current node and then explore the left, and on the backtrack, explore the right subtree? I'm not going to bore you with another walkthrough, but the benefit here is that we can choose not to recurse to a child if it's, for example, lower than our lower boundary or higher than our upper boundary. And we can make that check at any given parent node. Let's go through an example. So we can explore node 10 first. It's in our range. Let's add it to our sum. And since node 10 is in the range, we'll explore the left and then the backtrack the right subtree, but first, the left subtree. Here, we ask the same question. 5. Is 5 in the range? No, it's not. However, do we explore the left subtree? It turns out we do not here. And that's because we're in a BST. If the parent node of 5 is already lower than our lower bound, then there's no possible node in its left subtree, namely the 1 and 3, that is higher than it. This is the definition of a binary search tree, and we choose not to recurse to the left at all. This means we're more efficient and we don't have to process every single node. That said, do we explore the right subtree? Yes, we do. And that's specifically because 5 is still less than the upper bound. That means its right subtree may have nodes that are in between the range, aka nodes that are greater than 5, but less than our upper bound. And you'll see that obviously 6 and 7 fit that memo. Add node 7. Is it in between our range? Yes, it is. You add it to our range, you get 17. And then we choose to explore the left or right depending on the mentioned criteria. Is 7 in between our range? Fantastic. That means its left subtree may have a node in range. At node 6, it totally is. Let's add it. You get 23, which is the answer. Eventually, you backtrack up to 7. Do you explore the right? Well, you can, but in this case, there's nothing there. So you're not going to. So yes, the time complexity is still big O n, but in the best case, it is log n in the situation where our binary search tree is perfectly balanced and our ranges are in such a way where we just explore one node on each level. But hold on, there's a third solution, and it's an iterative version of our pre-order CLR solution. I'm actually going to opt for this one since Meta prefers this method and will typically ask you mid-interview to implement the iterative way. Not always, but for the most part, yes. So how do we do this? Let's walk through it. So to kick off our algorithm, I'm going to push the input root node, node 10, into a stack as to mimic backtracking in recursion. So here is that node. We ask the question, as always, is 10 in between our two boundaries? Yes, it is. We'll add it to sum. Once we do that, we can pop node 10 and see if we want to explore its children. Let's take a look at the right child. Do we explore the right subtree? Well, at least node 15 is not null. At least it has that going for it. But a second condition is not satisfied. 10, our current node, is already equal to our upper bound. What that means is, because we're in a BST, nothing to its right is going to be in range. The smallest number its right child can be then is 11. And 11 is obviously greater than 10. We can't have that. Therefore, we're not adding any of these nodes to our stack. We're actually going to not explore the right subtree at all. And our algorithm is slightly more efficient because of that. However, let's look at our left subtree. Is that a candidate? Well, node 5 is not null. And the difference here is that node 10 is still greater than our lower bound. That means in our left subtree, we have a chance of encountering a node 6, 7, 8, or 9, any of which are obviously in between our range. So what are we going to do? We're going to add node 5 to our stack and move on in our loop. And our loop, by the way, is a while loop in which we'll keep looping as long as the stack is not empty, as long as there are nodes that are candidates in between our range. At node 5, is it in our range? No, it's not. Let's pop it. Let's explore the two children. On the right subtree, 5 is lower than upper bound, so there might be candidate nodes in the right subtree. Let's push the right child of 7 to our stack. Let's explore the left subtree now. Great, node 3 is not null, but 5 is already lower than our lower bound. That means everything in the left subtree is also even lower, and thus not candidates. Let's X that out and choose not to add any of those nodes to our stack. Continuing on, we're at node 7, right? That's at the end of our stack. Node 7's in range. Let's add that to our sum variable. Remember to pop node 7, and then now we can explore its two children. Well, we have a null pointer on its right, so we don't add that to our stack at all. However, 7 is greater than our lower bound of 6, so we add 6 to our stack. As the last iteration in our while loop, 6 is in range, add that to our sum, pop it from our stack, and there's nowhere else to go. To summarize, the time complexity is big O n, but you can see how if this was a perfectly balanced tree, that we only really explored one node per level, that's best case of big O log n. As for space complexity, it's also big O n because of our stack. Okay, awesome. Let's get into the code. Okay, so what's the first order of business? We want to ready our variables. We're going to have a sum of 0 and a stack of our tree nodes, like so. To kick off our algorithm, we're going to push the root node and get into our while loop. Remember, we want to keep looping as long as the stack is not empty, as long as it's full of candidates that might be in our range. On each iteration, what do? Well, let's get a hold of our candidate node. Let's pop it so you don't have an infinite loop. Then we ask the age-old question, is our current value within the range of our boundaries? If it's higher than our lower boundary or equal to, and if it's lower than or equal to our upper bound, we're just going to add it to our sum, like so. After that, we'll explore the two children. Remember, there are two criteria. Let's explore the right subtree first. If the right child is not null, and the current node is lower than the upper bound, then the right child is potentially a candidate. Let's add it to our stack. Inversely, we're going to do the same check on the left subtree, that if the left child is not null and the current value is higher than the lower bound, then we'll also add it to our stack. After the loop is done, we're just going to return the sum, and that is the code. Okay, let's get into the variant. Okay, so what if instead of returning the sum, we had to return the average of all the nodes between the same lower and upper boundaries? Let's take a look at our example. So to find the average, we still need the same sum variable, right? And just looking at our tree, I'm not going to go through the workflow again, but 10, node 7, and node 15 are all within range of our lower and upper bounds. If we add all those to our sum like we did before, which by the way, we'll be using the same stack algorithm to do so, we get 7 plus 10 plus 15, that is 32. But as we're iterating through each node, there's another variable we need to keep track of, and that is the count, which is basically the number of nodes within the given range. In other words, when we encounter node 10, yes, it's in range and thus we add it to our sum, but we're also going to do one more thing. We're going to increment our count variable from 0 to 1. We're going to do the same thing when we encounter 7, we get 2, and lastly, node 15, from 2 to 3. There are 3 nodes within our range. And if we have the numerator to be 32 and the denominator to be 3, then we can compute the average to be 10.667 approximately. That's our answer. I will say with the average or the mean, the answer might not always divide evenly. So be careful about this in the interview, and you might want to use a double or a float so that your result doesn't truncate. To do that, you can just change your sum variable and or your count to be a double or float, and you'll be okay. Other than that, we can reuse our algorithm from earlier and just make a few changes for the variant. Okay, let's go into exactly how we're going to do that. Okay, what changes must we make? Well, for one, the method signature is going to return a double now, and so is our sum. Let's introduce that new variable. Let's call it count. And if we have those two, we can just return the sum divided by the count. Now on line 12, we add the current value to the sum should it be in range. We're still going to do that, right? But we now want to increment the count as well. And with that, surprisingly, that's all we have to do. This variant is not that much harder, but the next one is a bit nuts. Let's go into it. Now, there is a much tougher variant. I will say, though, that Meta doesn't ask it too often, but it's still fair game. And if you want to cover all your bases, keep watching. Okay, so the variant is, what if we wanted to find the sum just like we did in the original LeetCode problem, but we wanted to be able to find the sum between all sorts of ranges? We possibly want to find the sum between the ranges, say, 5 and 16, maybe another time where the lower bound is 0, upper bound is over 9,000, etc., etc., etc. The point is, we could be calling this function hundreds, if not 1,000 times. This is an important note that pretty much changes the entirety of the algorithm. The question boils down to, how would you change your code to be more efficient and to accommodate for this requirement? Let's reinspect our example from before. Clearly, we do not want to use our stack solution, right? We'd have a time complexity of big O(n) each and every single function call. I mean, if we had upwards 1,000,000 nodes, that's not very performant. But maybe we can pre-compute up front. Maybe we can parse the whole tree to make our 1,000 function calls much faster. And it's true though, pre-computing up front costs big O(n). You got to go through each node. But the deal is, we're only doing this once in the beginning. It'll pay off when we run the function however many times after. But the question is, what data structures would be useful to store ahead of time? Let me suggest this. If we preserve the node's values in ascending order in a vector, and a prefix sum of the node values in another vector, then if we had a lower bound of, say, 5 and upper bound of 16, can't we find the two boundaries of nodes closest to these two limits? For a lower bound of 5 within our vals vector of values, that would be the 5. For an upper boundary of 16 in our vals, that would be 15. Because 16 does exist, 15 is the next closest one that is lower than our upper bound. And if we find these two boundaries, can't we find the difference between their respective prefix sums? That, in other words, if the sum of all nodes up to and including node 5 is 9, and the sum of all nodes up until and including node 15 is 60, then isn't the difference between them the answer? Let's explain that a little bit more. Recall that, by definition, a prefix sum of a particular node is the sum of itself and all the nodes before it. Thus, the prefix sum of node 5 is 1 plus 3 plus 5. That yields 9, a prefix sum of 9. Likewise, for node 15, its prefix sum is the addition of 15 and all of the numbers before it. That yields 60, and you can check it if you want. 1 plus 3 plus 5, 6, 7, etc. up until 15, and including 15, you get 60. So if you know those two numbers, you can just subtract the difference to get the answer. However, there's one tricky thing to note here. If we minus these 3, we don't actually want to remove the 5, because that is actually within our range. And recall that our range is inclusive. This means we're going to minus 60, or in other words, the sum of all nodes up until and including node 15, as denoted up here, minus the sum of all nodes of the node before node 5 of our left boundary. Let's note that here. So if we chop off nodes 1 and 3, then we consider node 5 in our sum of all values of nodes within the inclusive range. 60 minus 4 then is 56, and that's our answer. And we can prove that as well. 5 plus 7 and 6 plus 10 and 13, we don't consider 18 because that stretches beyond our found right boundary, as you can see here. Then, if you add all this up, you do indeed get 56. Let's take another example. What if instead of a lower boundary of 5, we have a lower boundary of 0? And instead of an upper bound of 16, let's say we have 9. Okay, first things first, let's find the left boundary of the node that is closest to our lower boundary, or if it's not found, the next greatest one. Here, as you can see, there is no 0. The closest one, though, that's above it is 1, so that's the left boundary. As for the right boundary, obviously there's no 9 either. 7, however, is the next closest one that is below our upper bound. Sure, the 10 is closer, but remember, anything beyond our upper bound is invalid and not in range. So the sum up until and including node 7 is 1 plus 3 plus 5 plus 7 is 22. That's this entire portion. So we want to minus 22 from one node before 0. But hold on, there's nothing before it. This is the 0th index. This is the first number. This is an edge case. What we want to do here is if our lower boundary is at index 0, we just want to minus 0. Because it's the first node, there's nothing before it that's smaller than it, like a -1. We just need an if statement for that. Ultimately, we have 22 as our answer. Let's double check our work. If we have 1, 3, 5, 7, and 6, sorry, we had 6 before as well, then add it up, we get 22. The difference is just that. You also may be wondering two things. One, how do we even pre-compute these two vectors in the first place? Well, it's quite simple. Recall that we suggested an in-order traversal as the first solution to the original LeetCode problem. It wasn't efficient there and is quite naive, but it's suited for this use case here. Iterating through the nodes from the lowest value to the highest value is exactly what we want here. And each time we encounter and process a current node, we add it and push back to our values. Every time we do that, we're going to also compute its prefix sum. So in this case, when you encounter 1, you push the 1 here, but also add it to everything before it. However, the prefix sum at that point is empty, so you're just going to push a 1. This will manifest as an if statement. After that, the next node you process is a 3. You push that and you add it to the sum of all nodes before, which is just 1 to get 4. You kind of get the point, but let's go through one more. The next node you process is 5. Push the 5. You add the 5 to all the nodes beforehand. That's 4, right? That's 1 plus 3 is 4. So 5 plus 4 is 9, and you keep going all the way up until the end. The second question you may have is, well, finding the left and right boundaries, I mean, aren't those both big O(n)? Isn't that the same time complexity as before, as iterating through every single node every time? Well, this is where binary search comes into play, where we can find these in log n time. And it's actually very applicable here. You have a lower bound of 1 and an upper bound of 18, and everything in between is completely sorted. Okay, I'm sure you're very familiar with binary search, and this is quite redundant, but let's go over an example real quick. Let's initiate our 2 pointers, and for this example, let's find the right boundary. So ultimately, it'll be this number right here. You find the midpoint. Fantastic, you're at the 7. 7, comparatively, is lower than the 9. That means there might be a number somewhere to the right that is an 8 or a 9. We don't know that for sure, but we just know the answer is somewhere in this space, which, by the way, might include the 7, and we see in this case it absolutely does. Therefore, we can remove this whole space to its left and recurse to the right. Let's set the left to middle plus 1 and continue our search. The middle would next be 6. 13, however, is way too high relative to our upper bound. Therefore, we can discard this whole space here and set the right pointer to middle minus 1. That's going to be here. The left pointer remained the same, exactly where it was, and we calculate the middle to be, it's hard to see, but index 5. A 10 is also too large, so we go to the left again, thereby discarding this space. That puts R at index 4, and L remains the same at index 5. Well, the 2 pointers cross each other, where R, it ends up, is our answer, which is at index 4 for a value of 7 as our right boundary. It's a bit messy, but that is the premise of the algorithm. It'll be a lot more clear when we code it up. Let's get into it. Okay, so the first order of business, let's initiate our 2 vectors, right? We call them vals for values, and another vector of ints for the prefix sums. Let's also write an in-order traversal that takes in the root node, and it will go through the process of encountering each node in ascending order. Recall real quick that in order is LCR. You're going to go to the leftmost node first. Notice that, hey, the left child of 3 doesn't exist. That's a base case. We're just going to backtrack from there. So we're going to say if the root is null pointer, then we can just return. Otherwise, as you just saw, we're going to recurse to the left as much as possible. Now on the backtrack, for example, at node 3, we're going to process it and add it to our vals, but also add it to our prefix sums. Remember, a prefix sum, we add the 3 to everything before it. There's nothing before it, so if it's the first encounter, you just add whatever value it is, which is 3. After that, you're going to go to the right subtree, in which case there's also nothing. Let's code all that logic out. So we're going to push back to our vals, like so, and then have an if statement. If our prefix sums is empty, well, we just want to push back whatever value it is. In the ordinary case, you're just going to push back the actual prefix sum. That is, you can use the back function plus the current value. The back function will give you 3 when you're processing node 5, and you're saying, okay, well, the 5 that I pushed the vals plus the 3 is 8. You keep going, eventually you backtrack to the 10, you push the 10, and you add the 10 to the sum of all nodes before, which is 8. That's 18. Then after that, you recurse to the right subtree. Let's make sure we have that in our code. Lastly, on node 18, you're going to add it to vals, but also get the prefix sum, which is 36. Let's make sure we call this in-order method upfront one time in the constructor, and there, it's pre-computed. The next thing we want to do is find both boundaries, right? The right boundary in relation to the upper range. Let's call that function for the binary search find right boundary. We're going to pass in the 0th index as well as the last index and then the upper bound. In this case, if I draw out the indices and say the upper bound is 12, then I need to know the 0, the 3, and the 12 to eventually find that the right boundary is 10, whose index is 2. Now, you can use some sort of algorithm to do the binary search, but I'm just going to implement it out. Let's call it the left pointer, the right pointer, and the upper. We're going to have our while loop and keep looping as long as the 2 pointers don't cross, which we call in the earlier example, we return wherever the right pointer ends up. In each case, we want to find the middle. That's the calculation of the right minus left divided 2 plus the left. If the value at that middle is lower or equal to the upper, well, we want to go to the right. There might be a better, closer candidate there. Otherwise, we're just going to go to the left. There you go, pretty self-explanatory. I'm actually going to collapse these just so we can see the code that we're writing a lot better. Let's also write the left boundary method very quickly. We also need the left, right, and lower bound this time. I'm going to do a bad thing and copy and paste from the previous example. And with this, there's a small tweak we need to make. That is this sign when we compare it to the lower bound. And if that's the case, we want to swap these two operations like so. Don't forget to return left instead of right. And there you have it. I will say copy and pasting during an interview might save you a lot of time, but with the trade-off of very error-prone mistakes. And if you make that, it could be devastating. So consider your trade-offs. Okay, with that, let's collapse that as well and write the function call for the left boundary consistently. Let's call it left boundary. It's going to be this function name, and instead we want the lower boundary. With that in mind, both those calls in log n, we got to take care of an edge case. What if the left boundary is at the 0th index? Well, there's no element before that, so we can just return prefix sums at the right boundary index. The ordinary case, where we found the delta, it's going to be the prefix sums at the right boundary minus the prefix sums at the left boundary minus 1 position. And there you have it. With an upfront cost of big O n, you can now call your function 1,000 times, in which case the time complexity would be log n times 2, but really it boils down to just log n. The space complexity is big O n times 2, which is just big O n. And that is it. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.